I'm Naoya Ozaki, the assistant professor of ISAS JAXA. Before going that, I just get my PhD 2.5 years ago. And then before that, I was a student of University of Tokyo, and I spent almost all the time to developing the deep space micro nano spacecraft. Especially, I spend a lot of time for this mission, the Procyon, which is explained by Dr. Professor Nakasuka. But why I am one of the system design member of Procyon mission, and then after that I started working on the Icurius mission, which is shown in the middle of this figure, and then explained by the Professor Nakasuka. But this is from the other institute or university, but this is kind of a lineup of deep space CubeSats. So this is the key topic of this presentation. And then, so the one of the other key topic is the Lunar Orbital Platform Gateway. And then this gateway, or what we call gateway, it's gonna start constructing quite soon. And then we can utilize this deep space station for our mission objective. So the beginning of this gateway, is the NASA's Artemis 1 mission. And starting from this NASA's Artemis 1 mission, we can expect that more than 10 CubeSats are launched to the deep space every year. So I cannot promise this, but I just simply extrapolate the current situation. So NASA's Artemis 1 carries 13 CubeSats at the same time. And then considering the upcoming schedule, the NASA will launch the similar size of launch vehicle almost every year. And also the other country or commercial partner is going to launch the launch a rocket to the moon. So that's why I think this is in all likelihood this kind of things will happen. So there is a good opportunity to launch the many CubeSats to the deep space. Okay, and the current situation, maybe for example, JAXA can launch only one spacecraft every 2 years. So one deep space probe every 2 years. Okay, and 10 CubeSat every year is significant difference. So so we can expect that the similar innovation that is happening in Earth orbiting satellite is also similar innovation will also happen in the deep space missions. As I said, there is a good opportunity, but in the current capacity, I don't know whether we can fully utilize this opportunity. But considering, for example, UNISEC has developed a lot of spacecraft CubeSats so far. Most of that is to launch to the Earth orbit, but there is a lot of heritage to develop CubeSats. If you can use this heritage, I'm proud. I mean, I think we can actually make this opportunity true. So the key topic, key message of my presentation is let us use this heritage, and let us make that dream come true. Okay, so what is a Lunar Orbital Platform Gateway? So LOPG or Gateway is a planned space station launching to the lunar orbit. And then NASA's Artemis program plays a major role to develop this gateway, and with collaboration of commercial and international partners, including ESA, JAXA, CSA, Roscosmos, and so on. So this gateway is gonna develop on the lunar orbit, but where it is in the near rectilinear halo orbit around the moon. So I'm going to explain what is a near rectilinear halo orbit later. but it's a kind of a halo orbit under Earth-Moon gravity. Okay, to understand what is a near rectilinear halo orbit, we have to understand the Lagrangian point or Lagrange point. The Lagrange point is the equilibrium point where the Earth's gravity and the Moon's gravity and the centrifugal force balance each other, like this point. So considering a three-body dynamical system, we know that there are 5 types of Lagrangian point exist in each three-body dynamical system. Okay, so let's consider the Earth-Moon three-body dynamical system. Then we have 5 Lagrangian point. If we consider the Sun-Earth three-body system, there is another 5 Lagrangian point. Okay, so this is a geometry of Lagrange point. As you can see, here is the Earth, and then the Sun is the left side. So this is a Sun-Earth fixed rotation. So I draw this figure in the Sun-Earth line fixed rotational frame. Yeah, and then here is the Moon. Okay, so there is a 5. If you consider the Earth, Moon, three-body dynamical system, there is 1, 2, 3, 4, 5 Lagrangian point around this three-body system. And then if you consider the Earth, Sun, Earth three-body system, there is 1, 2, and 3, 4, 5. Sorry, the 3, 4, 5 Lagrangian point is out of this plot figure, but there is a 5 Lagrangian point in the Sun-Earth system too. Okay, if you consider the cis-lunar region, so it's the region very close to both Earth and the Moon, the geometry is like this way. Okay, so there is 5 Lagrangian point related to the Earth, Moon, and there are 2 Lagrangian point related to the Sun and the Earth. And the gateway is here. So Earth, Moon, L2 Lagrangian point. Okay, so this is a YouTube video. I think you can find this as the same one in the YouTube. But this is the quick explanation of what is a near rectilinear halo orbit. Okay, here is the Earth and Moon and L1 point and L2 Lagrangian point. Sorry. Okay, so wait a sec. So in this Lagrangian point, we can find the periodic orbit around Lagrangian point. We called halo orbit, and then this plot is we draw the halo orbit in the different energy. Okay, so this color map is the energy. So if we change the energy, we can draw the multiple halo orbit around the Earth-Moon system, and then some of the closer to the Moon. So this orbit. So we call this orbit is near rectilinear halo orbit. Okay, and then there is 4 different type of near rectilinear halo orbit, but gateway is put it on the L2 type of near rectilinear halo orbit, and then the closer to the closest perilune at North Pole and apollune at South Pole. Okay, so this kind of orbit. Okay, Earth is here and Moon is here. If we look at the trajectory orbit in the Earth-Moon fixed rotational frame, the near rectilinear halo orbit of the gateway is looking like this orbit. Really like an elliptic orbit, but this orbit is only found in the three-body dynamical system. Okay, so this is a characteristic of near rectilinear halo orbit. So the one of the important characteristic is a geometric relationship to the Earth is always the same, and then there is no you know, in terms of communication, it's really preferable. And also, this is a type of halo orbit, as I said. And then halo orbit is unstable, which means they're easily reachable and also escapable. Okay, so the accessibility to this near rectilinear halo orbit is really good. And then also, if we select appropriate energy or period of this orbit, we can find which we call synodic resonant NRHO. And in this orbit, the station never experience eclipse. So there's no power issue. Okay, so this is why we select this NRHO for the gateway mission. So not only just utilizing gateway, we can utilize the construction opportunity of this gateway. Basically, I think the construction opportunity is this construction opportunity, the spacecraft is launched and inserted to the lunar transfer trajectory or lunar transfer orbit, like this figure, this plot. Okay, as was the case of Artemis 1 mission of Eclipse or another 13 CubeSat. So in this orbit, we can do the lunar swing by at this point. And then if we can do appropriate orbital control maneuver, we can change the trajectory of spacecraft appropriately. And then we can fly to the interplanetary space or periodic orbit or many other type of trajectory. Okay, so this is a basic mission scenario utilizing this gateway construction opportunity. The spacecraft is launched and separated to the lunar transfer trajectory. And in this trajectory, after separation, we have about 1 week. And then after 1 week, we're gonna have lunar swing by. Okay, so we have to do trajectory correction maneuver, which is about 20 meters per sec. Okay, and then this is a really reasonable number for the CubeSat. And then I would say that if the 6U CubeSat, I think this number is really capable. 3U CubeSat is, I think it's a bit hard, but more than 6, if the spacecraft is more than 6U CubeSat, I think this is capable number. Okay, so and then this is also, and then using lunar swing by, we can go to the lunar orbit or lunar surface or Earth-Moon Lagrangian point or Sun-Earth Lagrangian point or interplanetary space, if you like. And then I think, so I cannot promise again, but this is also the possible mission scenario for the early Artemis opportunity, such as Artemis 2 or later. So I'm going to explain the how can we design the trajectory to go to the Sun-Earth L1 Lagrangian point or to the lunar surface or to lunar orbit or Earth-Moon Lagrangian point or interplanetary space. Okay, so let's start from the first one to the Sun-Earth Lagrangian point. So as I said, that there is the periodic orbit around Lagrangian point. Okay, and like this kind. So this is here is L1 Lagrangian point of Sun Earth system, and this is a kind of periodic orbit around this Lagrangian point. And then we know that there is a manifold structure related to this periodic orbit around the Lagrangian point. So what is a manifold structure? So I'm going to explain this, but because this periodic orbit is unstable, even if a very, very small, tiny delta V maneuver, the spacecraft trajectory is disturbed. And then if we add a small delta V maneuver at each different phase on the periodic orbit, we can draw this kind of tube structure. If we propagate trajectory, we can draw this kind of tube structure. And then basically, the spacecraft will leave this periodic orbit on this group of orbit called unstable manifold. Okay, so starting from here and then adding very tiny maneuver, the spacecraft will escape to this direction on this unstable manifold. There are two directions to escape. Because of this symmetry, the spacecraft can also asymptotically approach to this periodic orbit by riding this stable manifold. And then we can insert the spacecraft to this periodic orbit with very tiny delta V. So to transfer to the Sun-Earth L1 or L2 Lagrangian point, we should just select the one single trajectory on the stable manifold. Then we can ballistically, so this is stable manifold, and then just select one of the trajectory on this stable manifold. Then the spacecraft can ballistically transfer to the periodic orbit around the Lagrangian point. Okay, and then the second case is a lunar surface. So the first one, basically we don't need delta V, where strictly speaking, we need a small number of delta V, but almost nothing. But second one, to the lunar surface, we need a large delta V. So to calculate this delta V, we can just use a two-body problem Pachyconic assumption. So, and then I think some of you may know, but in the vicinity of the moon, we can consider the orbit is considered as with respect to the moon. And then using orbital energy invariant conservation law, this law, we can calculate the velocity at lunar surface. Suppose that the V infinity is this number. This is example of Artemis 1, and then radius is on the lunar surface. Then the delta V, the velocity is 2.5 kilometer per sec. So basically, in order to land on the moon, we need to cancel this velocity. So that's why the delta V is about 2.5 kilometer per sec. Of course, we can use the lunar rotation, but it's quite small. So basically, this number is the good assumption. So, and then JAXA's Omotenashi mission is trying to do land on the lunar surface using 6U CubeSat, but 2.5 kilometer per sec is really, really hard. I mean, Omotenashi is trying to do, but it's really difficult mission. Okay, so the third one is to lunar orbit or Earth Moon L1, L2 Lagrangian point. So we can choose two options. The one option is direct insertion. The other is low energy transfer and capture. So for the direct insertion, we can just use the Pachyconics or two-body problem, and which is used, I mean, like the same way as what we have done in here. We can estimate the delta V is about 0.5 to 1 kilometer per sec. Well, it's still really challenging for the nano micro spacecraft, but I think it's a doable number. But there is alternative way to use using low energy transfer and capture utilizing solar tidal force. Okay, so using solar tidal force, we can effectively reduce this number of V infinity. You know, at this point, V infinity with respect to the moon is 1 kilometer per sec. But using a low energy transfer of solar tidal force, we can reduce this V infinity to almost 0. And then we can insert to the, for example, hello orbit without delta V. In the case of NRHO, we need, for example, 10 meter per sec delta V. It's really small, but it's a capable number for 6 CubeSat. Okay, and the solar tidal force is basically if you pass through the Lagrangian point or Sun-Earth Lagrangian point, we can effectively utilize solar tidal force. Okay, here is Earth, and then this is Moon orbit. So this is a Grail trajectory, but in the case of Grail, it's gonna fly to the near L1 Sun-Earth L1 Lagrangian point, and then reduce V infinity to the Moon, and then insert to the Moon. Right figure is Eclipse trajectory as an example. Eclipse is also use this similar type of orbit, and then in the case of Eclipse, we just need about 10 or a bit more than 10 meter per sec delta V to insert to the near rectilinear halo orbit. Okay, and then to the interplanetary space, for example, like Mars and asteroid, we can utilize solar tidal force in the inverse way. So in order to increase V infinity with respect to the Moon, we can also use solar tidal force. So this is a case of Destiny's trajectory, but basically, if the spacecraft flying at vicinity of L1 Lagrangian point, we can increase the V infinity with respect to the Moon. And in my experience, we can increase the this V infinity is about up to 2.5 kilometer per sec. And then in this case, the Earth escape V infinity is about 1.5 kilometer per sec. So this is where in my experience, this 1.5 kilometer per sec is a kind of maximum number. So
Dr. Ozaki, you have 5 minutes.
Okay, I see. So this 1.5 kilometer per sec V infinity. So I'm gonna explain what is this number, what this number means. So this is a table which summarize required V infinity at the Earth departure. If we want to go to the Mercury, we need about 7.5 kilometer per sec. You know, it's quite large compared to the 1.5 kilometer per sec. So it means it's really hard to get to the Mercury. So in the case of Venus, it's 2.5, but it's still we need a more delta V. So we need a more V infinity. The asteroid, it's depend on which asteroid, but there is definitely reachable asteroid using this just 1.5 kilometer per sec. And the Mars, it's also a bit hard. So if you look at this chart, you may see and you may find that most of the planet is difficult to access. So to increase the infinity, one of the options is utilizing a V infinity revelation transfer, or we call the delta vega or ED vega. And using this maneuver, we can effectively increase as this departure of infinity. And then the right plot is the example of infinity leveraging transfer to go to the Mars. So if you want to increase this infinity from 1.5 kilometer per sec, which is at escape point, to the 3.0 kilometer per sec, which is reachable to the Mars. So basically, so in this calculation, we need a 0.83 kilometer per sec. So basically, if you want to increase the infinity, we need a half of the infinity increment. We need a delta V, which amount is about a half of this delta V as an infinity increment. Okay, in the end, we can write this kind of gateway metro map. So I think we can utilize this metro map for your mission if you like. So I think I can give this metro map later in the PDF. So I think you can check it later, but basically the gateway is a really good point to transfer to almost everywhere. So that is why we are planning to put gateway here. Okay, so almost final slide. So the possible mission utilizing the Lunar Orbital Platform Gateway is to Moon. The Moon orbital mission is the possible. The asteroid flyby mission is also possible. And then to go to Lagrangian Point mission, it's really possible. So that if you want to go to the Mars, Venus, or rendezvous to the asteroid, or soft landing on the Moon, this is quite challenging at this moment, but in near future, I believe it will be possible. Okay, in summary, so I explained what is a Lunar Orbital Platform Gateway, and then I explained that which orbit can the spacecraft transfer from lunar transfer orbit, which is for the gateway construction opportunity. And then in the end, I showed which type of mission can the small spacecraft do by utilizing this gateway opportunity. Okay, that's it. Thank you very much.